key insights from the latest reports and research, and basically get you up to speed fast.
And hopefully have a few aha moments along the way.
Exactly. Today we're tackling a really fundamental concept in science, emergence. You know, the idea that complex behaviors arise from simple parts interacting.
Right, like think about a single water molecule, H2O. It has certain properties, sure.
But it doesn't predict fluidity, does it?
Yeah.
Or surface tension, or, I don't know, the amazing patterns in ice crystals.
Not at all. Those are emergent properties. They only appear when you have a whole bunch of water molecules interacting collectively. The whole is genuinely more than the sum of its parts.
It's like the universe has these hidden rules that only show up when things get complicated enough.
Well, yeah. Physicist P.W. Anderson famously titled an essay, "More is Different." It's a cornerstone of condensed matter physics. New rules, new phenomena emerging from collective behavior.
And scientists sometimes talk about weak versus strong emergence.
Weak emergence is like, okay, in principle, you could derive the complex behavior from the simple parts if you had infinite computing power. But practically, it's unforeseeable. Strong emergence is, well, more controversial. It suggests truly new, fundamental aspects of reality pop into existence.
And condensed matter physics, studying solids and liquids, is just packed with examples, right? Like, why is a solid rigid? Or superconductivity electrons flowing with zero resistance.
Absolutely. Those are emergent phenomena, Cooper pairs and superconductors, magnetism. But today's deep dive is really exciting because we're moving beyond just observing emergence.
We're engineering it. That's the focus, right? We're looking at a report on Moiré Superlattices, a platform where scientists are kind of building emergence from the ground up.
Precisely. Moiré superlattices are a massive paradigm shift. Instead of finding emergence in nature, we're designing materials to create specific emergent quantum phenomena. It's quantum engineering, really.
And the big bang for this field, the thing that really kicked it off, was that discovery in 2018, the magic angle.
Yeah, that was the watershed moment for twistronics. Researchers took 2 sheets of plain old graphene, basically pencil lead, just 1 atom thick, stacked them, and twisted one layer relative to the other by about 1.1 degrees.
Just 1.1 degrees. Seems tiny.
It is. But that tiny twist completely transformed the graphene. Suddenly, this simple material became a playground for incredibly complex quantum effects, correlated insulating states, even unconventional superconductivity, things you'd never expect from graphene alone.
Wild. So how does this work? How does stacking and twisting these 2D materials like graphene or TMDs?
Transition metal dichalcogenides, yeah, like tungsten diselenite, things like that.
Right. How does that twist act as this, like, control knob?
Okay, so when you stack 2 2D crystal lattices, and they're slightly misaligned either by a twist angle or because they have slightly different atomic spacing, a lattice mismatch, they create an interference pattern, like when waves overlap.
A Moiré pattern, like you see sometimes in fabrics or screen doors?
Exactly that visual idea. But here, it's an atomic scale interference pattern that creates a new, much larger periodic landscape for the electrons. This is the Moiré superlattice.
How much larger are we talking?
For small twist angles, the Moiré periodicity, let's call it D, can be tens of nanometers, while the original atomic spacing A is, fractions of a nanometer. The formula for twisted bilayer graphene is roughly D equals A divided by 2 times the sine of half the twist angle. So tiny angles mean huge D.
Wow. Okay, so 1 unit of this new Moiré pattern can contain thousands of original atoms.
Thousands, yes. It's creating this giant artificial crystal lattice, but one whose properties we can tune by changing that twist angle.
Is it just a perfect overlay, though? Or do the atoms themselves react to this new situation?
Good question. No, it's not rigid. The atoms actually relax. They shift their position slightly to minimize the overall energy. This is called atomic reconstruction.
So they kind of settle into the most comfortable spots in this new Moiré landscape.
Sort of. They form large domains where the stacking is energetically favorable, like the AB or BA stacking in graphene. And these domains are separated by boundary lines, shear solitons, you could call them. It's like wrinkles forming.
And that rearrangement is important.
Critically important. It's an emergent structural phenomenon itself. The atoms rearrange, and that rearranged structure then feeds back and defines the electronic landscape the electrons experience. It's a loop.
Okay, so structure changes, and that changes how the electrons behave. How does it affect their energy levels, their bands?
The Moiré superlattice imposes its long wavelength periodicity on the electrons. Quantum mechanically, this leads to band folding. Imagine the original electronic band structure, which describes electron energies versus momentum. Now, because the repeating unit cell is much larger in real space, the corresponding momentum space, the Brillouin zone, becomes much smaller.
Okay.
So you take the original bands and effectively fold them, like folding a map, into this new, smaller mini Brillouin zone. This process creates new Moiré minibands.
And the key thing about these minibands is?
They are often incredibly narrow in energy range. Their bandwidth is dramatically reduced compared to the original material.
Which leads us to the famous flat bands, right? Why is flat so important here?
Ultra-flat bands are maybe the most crucial outcome. Flat means the energy barely changes with momentum. In classical terms, it means the electrons have almost zero kinetic energy. They're hardly moving.
So they're kind of stuck.
Effectively, yes. And when kinetic energy is quenched, the interactions between electrons, the Coulomb repulsion, how they push each other away, suddenly become the dominant energy scale. They can't just zip past each other anymore.
Ah, okay, so interactions take over.
Precisely. This drives the system into a strongly correlated regime. And that's the fertile ground where all these amazing many-body quantum phenomena start to emerge. The interactions dictate everything.
And the magic angle in graphene, the 1.1 degrees, that's just a particularly good way to get these flat bands.
It is. For twisted bilayer graphene, at that specific angle, quantum interference effects between the layers cause the electron velocity to vanish at certain points, leading to exceptionally flat bands. And it's not just one angle. There's a whole series of discrete magic angles at smaller twists.
But it's not only magic angles, right? Flat bands can happen in other ways in these systems.
Absolutely. Flat bands are actually a pretty generic feature. In TMB heterostructures, for example, you can get flat bands over a continuous range of small twist angles due to strong intrinsic interactions and how the bands align. You don't need that precise magic angle tuning.
So the magic angle was maybe the first big discovery, but the principle is broader.
Exactly. And you could even use external things, like applying mechanical strain to flatten bands at other angles. The core idea is Moiré-induced localization, using the Moiré pattern to trap electrons and make their interactions dominant. The twist is just one very effective way to do it.
Okay, so we've engineered flat bands, electrons are localized, interactions rule. This is sort of level 1 emergence. Now, what happens at level 2? What kind of states emerge from this strongly correlated soup?
Yeah, now things get really interesting. It's like unleashing a zoo of competing quantum phases.
Yeah.
Because the kinetic energy is so low, subtle energy differences matter, and you can often tip the balance between different states just by changing the electron density with a gate voltage or applying fields.
Let's start with insulators. The report mentions correlated insulators, where interactions stop electrons from moving, even when basic band theory says they should. Two main types.
That's right, a tale of two interactions, as you put it. In graphene-based systems, like magic angle twisted bilayer graphene, we often see insulating states right at integer fillings, say 2 or 3 electrons per Moiré unit cell. These behave like Mott insulators.
Mott insulators. That's driven by short-range repulsion.
Primarily, yes. The strong Coulomb repulsion makes it energetically costly for 2 electrons to occupy the same Moiré site. So they localize, 1 per site, creating an insulating gap. It's like seats on a bus, everyone takes one, and no one can move easily.
Okay, that's Mott. What about the other type, generalized Wigner crystals?
These are more prominent in the TMD heterostructures, like stacking WS zeros on WS zero. Here, you see insulating states not just at integers, but also at fractional fillings, like 13 or 23 of an electron per Moiré site. These are generalized Wigner crystals, GWCs.
Wigner crystals, isn't that where electrons form an ordered lattice themselves?
Exactly. In GWCs, it's the long-range part of the Coulomb repulsion that dominates. To minimize this long-range repulsion energy, the electrons spontaneously break the symmetry of the underlying Moiré lattice and arrange themselves into their own ordered crystal structure. Triangles, honeycombs, stripes, depending on the filling.
Wait, you can see this electron crystal?
Yes. That's one of the amazing things. Scanning tunneling microscopy, SPM, has directly imaged these ordered electron patterns. You can literally see the Wigner crystal formed by the electrons.
That's incredible. So why Mott in graphene and Wigner in TMDs? What's the difference?
It boils down to the intrinsic material properties, amplified by the Moiré potential. Graphene has better dielectric screening, which weakens long-range interactions, and it has weak spin-orbit coupling. This favors the short-range physics of the Mott state.
Okay.
TMDs, on the other hand, have poor screening, so long-range Coulomb forces remain strong. Plus, they have strong spin-orbit coupling. These factors favor the electrons ordering themselves into a Wigner crystal to minimize that long-range repulsion.
So the Moiré platform lets you choose your material to emphasize different fundamental interactions. That's powerful.
So it's a key design principle.
All right, beyond insulators, the really big one, superconductivity. It shows up here too.
Oh, yes. And it's often found right next door to those correlated insulating states in the phase diagram. Typically, you start with the insulator, then add a few charge carriers, doping it, and superconductivity emerges in a kind of dome shape as you vary the doping.
That proximity suggests they're related, doesn't it? Like the same interactions causing insulation might also cause the superconductivity.
That's the prevailing idea.
Yeah.
It strongly points towards an unconventional pairing mechanism. The electron correlations responsible for the insulating state are likely also mediating the attractive interaction needed to form Cooper pairs for superconductivity.
So definitely not the standard textbook BCS theory.
For evidence strongly suggests not. For one, the way the superfluid stiffness vanishes with temperature often follows a power law, not the exponential behavior expected for simple BCS wave superconductors. What else? We see evidence for a pseudo-gap phase above the superconducting transition temperature, TC. This means some sort of energy gap opens up even before true long-range superconductivity sets in, suggesting Cooper pairs might be forming locally but aren't coherent across the whole sample yet.
Interesting, like preformed pairs.
Something like that. Also, the size of the superconducting gap compared to the transition temperature is often much larger than the BCS prediction. In magic angle graphene, ratios can be huge, like 25, whereas BCS predicts about 3.5.
So the mechanism is still a big puzzle.
It's a major area of research. Is it purely electronic correlations? Does the weird quantum geometry of the flat bands play a role? Or maybe coupling to those Moiré phonons we mentioned earlier gets enhanced? It's likely a complex interplay.
Okay, so insulators, superconductors. What about magnetism? Flat bands should help that too, right? Less kinetic energy means exchange interactions matter more.
Exactly. The reduced kinetic energy boosts the tendency for electron skins to align. We see this in twisted magnetic insulators, like chromium triiodide. Twisting two layers creates a Moiré pattern in the magnetic coupling between layers, leading to coexisting ferromagnetic and antiferromagnetic domains on the nanoscale.
So you can pattern magnetism with a twist.
You can. And in the TMDs, you can get itinerant magnetism from moving electrons, especially when the electron density is tuned near certain features in the band structure. Strong spin-orbit coupling in TMDs also plays a role here.
And then there was that really wild one, light-induced magnetism.
Yes. That's a truly remarkable finding in certain TMD Moiré systems, like WS0, WS0. These materials aren't magnetic normally.
Yeah.
But if you shine light on them at just the right frequency to create excitons.
Electron-hole pairs.
Right. Those photoexcited excitons can mediate an effective interaction between localized holes that triggers a collective ferromagnetic state. So you can literally switch on magnetism with a laser pulse.
That's mind-blowing non-equilibrium control.
Opens up huge possibilities for optical control of quantum matter.
Okay, let's move to topology. This feels like level 3 emergence, really exotic stuff. Quantum anomalous Hall effect.
Exactly. This is where things get really robust and protected. The combination of the Moiré potential and sometimes broken symmetries can engineer electronic bands that have a non-trivial topological character. This is often quantified by an integer called a Chern number, C.
And a non-zero Chern number means?
It means the material behaves in a fundamentally different way. The prime example is the quantum anomalous Hall QAH effect. You get a quantized Hall resistance, meaning resistance measured sideways to the current flow is perfectly fixed at h divided by c times e squared, where h is Planck's constant and e is the electron charge.
Like the regular quantum Hall effect, but without needing a huge external magnetic field.
Precisely. The topology of the bands itself generates the effect. This QAH state carries current along the edges of the sample in perfectly dissipationless chiral edge states. They only go one way. It's been seen in systems like specially stacked trilayer graphene on boron nitride and also in twisted TMDs like Moiré-engineered.
A perfect one-way street for electrons built into the material.
A very good analogy. Often it's intertwined with a type of magnetism called orbital ferromagnetism.
And there's a fractional version too, fractional Chern insulators.
Yes, FCIs. These are even more exotic. They happen when you take one of these topologically non-trivial flat bands with a Chern number and only partially fill it with electrons. The strong interactions can then drive the system into a state analogous to the fractional quantum Hall effect, but again at zero magnetic field.
Hosting quasi-particles with fractional charge.
Potentially, yes. In TMD moires, these can emerge when interactions force the electrons into a single valley, a specific momentum state, which then reveals the underlying topology of that partially filled band. What's amazing is the tunability. You can sometimes switch the Chern number of an insulating state with an electric field.
Incredible control. Okay, we focus on electrons, but you mentioned Moiré excitons and phonons earlier. Can we quickly recap those?
Sure. In the semiconducting TMDs, the Moiré potential creates nanoscale traps for excitons, those bound electron hole pairs. These Moiré excitons act like arrays of artificial atoms or quantum dots. They emit light at specific tunable frequencies.
So potential for quantum light sources.
Definitely. Things like single photon emitters for quantum communication or nanolasers. And the Moiré phonons, the new vibrational modes created by the folding of the phonon spectrum, are interesting too. They can be detected with Raman spectroscopy. And, as I mentioned, their potentially enhanced coupling to the flat electronic bands might even play a role in the superconductivity.
So let's try to summarize that hierarchy again. Level 1. The Moiré potential engineers the basic landscape, flat bands, Moiré excitons, Moiré phonons.
Right, sets the stage.
Level 2. Strong interactions within those flat bands take over, creating the primary ground states like Mott insulators or Wigner crystals.
The main correlated phases, yeah.
And level 3, you perturb or tweak those level 2 states, maybe by doping or applying fields, and stabilize the really exotic, often fragile phases like unconventional superconductivity or fractional Chern insulators.
That's a great way to capture the layered nature of emergence in these systems. It really is like discovering a whole new universe of quantum matter that we can build and explore.
It's fascinating physics, but it also sounds incredibly challenging to actually do. How do researchers model this, make these things, and measure these effects?
It's a huge interplay between theory, fabrication, and measurement, and each faces significant hurdles. The scales involved are tough, thousands of atoms in a Moiré cell, but the important energy scales are tiny milli-electron volts or less.
So how do theorists even approach this?
There are broadly two camps. On one side, you have continuum models. These are simplified, low-energy theories, like the Stritzer-McDonald model that first predicted the magic angle in graphene. They ignore the atomistic details and focus on the smooth Moiré potential.
Advantages.
They're computationally cheaper, you can sometimes get analytical insights, but they are approximations, and they often miss effects like atomic reconstruction.
And on the other side.
Atomistic models. These start from the real atomic lattice, using techniques like tight binding or density functional theory, DFT. They're much more accurate, they can capture lattice relaxation naturally.
Disadvantages.
They are computationally very expensive, especially for the thousands of atoms in a Moiré unit cell. Bridging the accuracy of atomistic models with the efficiency needed to explore complex phase diagrams is a major theoretical challenge. Developing better hybrid methods is key.
Okay, theory is tough.
Yeah.
What about actually making the samples with that perfect twist?
The gold standard right now is the tear and stack technique. You start with a pristine flake of 2D material, usually peeled off a bulk crystal using sticky tape exfoliation.
Like the original graphene discovery.
Exactly. Then you use specialized tools under a microscope to literally tear the flake in two. You pick up one half with a special polymer stamp, rotate it with incredible precision.
How precise?
We're talking better than 0.1 degrees of accuracy. Then you carefully lower it and stack it onto the other half, making sure the interface between them is perfectly clean.
That sounds fiddly.
It's extremely painstaking, requires a lot of skill and patience, and the yield of high-quality devices is often low. There are innovations, like using new types of polymers that are improving reliability, but it's still very much a craft.
So not ready for mass production yet.
Not with this method. There are alternative approaches, like chemical vapor deposition, CVD, which can grow 2D materials over larger areas, like wafers. But the crystal quality is often not as good, and controlling the twist angle uniformly over large areas with CVD is still a major challenge. That scalability is probably the biggest bottleneck for applications.
Okay, so let's say you manage to make one of these delicate, precisely twisted structures. How do you measure all the weird quantum stuff happening inside?
You need a whole suite of tools. Basic electrical transport measurements are fundamental, measuring resistance as a function of temperature, gate voltage, magnetic field. That tells you if it's an insulator, metal, superconductor, or if you see quantized Hall plateaus signaling topology.
Standard stuff, but crucial.
Absolutely. Then, for a local picture, scanning tunneling microscopy, STM, is incredibly powerful. An atomically sharp tip scans across the surface, allowing you to map the topography, literally see the Moiré pattern.
And you can measure electronic properties, too.
Yes, by measuring the tunneling current, you can map the local density of states, visualize the flat bands, and, as we discussed, directly image ordered electron states like Wigner crystals. Gives you real space insight.
Amazing. What else?
For the semiconducting TMDs, optical spectroscopy is key. Photoluminescence tells you about the Moiré excitons. Absorption measurements, techniques like magnetic circular dichroism can probe magnetism. Raman spectroscopy probes the Moiré phonons, the lattice vibrations.
And can you directly see the band structure?
That's the domain of angle-resolved photoemission spectroscopy, ARPES. It directly measures electron energy versus momentum, mapping out the band structure. It's experimentally challenging for Moiré systems because the features are often faint and require high resolution, and the samples are small, but it provides the most direct view of the electronic bands, including flatness.
So it sounds like there's this constant trade-off. Some techniques give you incredible detail locally, like STM, but are slow. Others are faster or work on larger scales, like transport, but give averaged information. And fabrication has this tension between precision and scalability.
That's a perfect summary of the methodological trilemma in this field. You're always balancing precision, scalability, and the depth of information you can get. Pushing those boundaries is where progress happens.
So pulling it all together, we've seen this incredible landscape of emergent quantum phases engineered in Moiré materials. What's the big picture view now? What are the key remaining questions and the most exciting future directions?
One major theme is understanding the interplay between these different quantum phases. They don't exist in isolation. They live together in complex phase diagrams, often competing or intertwined. A big goal is to map out these diagrams and understand the transitions between phases.
Like, how does a Wigner crystal melt into a correlated metal?
Exactly. Studying things like quantum melting or the precise relationship between the parent correlated insulators and the nearby superconducting domes, that's fundamental condensed matter physics being explored in a uniquely tunable system.
And the grand challenges we need to overcome.
Number one is definitely material quality and scalability. Making large area samples with uniform twist angles and minimal disorder is the single biggest hurdle for both fundamental science and any future technology. Without better materials, progress is limited.
Okay, materials first. What else?
Second is bridging theory and experiment more effectively. Real devices have disorder, strain variations, interactions with the substrate. Incorporating these non-ideal effects realistically into theoretical models that are already computationally demanding is a huge challenge.
Making the models match reality better.
Right. And third, a specific scientific goal. Truly unraveling the superconducting mechanism. Is it purely electronic? What's the role of phonons? Quantum geometry. Pinning that down could have implications far beyond Moiré materials, maybe even for understanding high-temperature superconductivity elsewhere.
Yeah. Despite the challenges, the future looks incredibly promising, though. Where is the field heading next?
Oh, it's exploding in multiple directions. People are exploring new Moiré platforms going beyond simple bilayers to complex multilayers, twisting materials that are already magnetic or superconducting to see how Moiré patterns modify those states, even creating Moiré quasicrystals with non-repeating patterns.
So expanding the Moiré toolkit.
Definitely. There's also a huge push towards dynamic and non-equilibrium phenomena. Not just studying the static ground states, but actively controlling them with light pulses, like the light-induced magnetism, or using periodic driving to create floquet topological states, or even studying how Wigner crystals might slide under an electric field. It's about making these systems dynamic and responsive.
Active quantum matter.
You could call it that. And related to that is the idea of using Moiré materials as quantum metamaterials or quantum simulators.
What do you mean by that?
Thinking of them not just as materials, but as platforms where the fundamental physics is dictated by the geometry, the twist angle, the stacking. You can potentially engineer them to simulate specific theoretical models, like the Hubbard model, which is crucial for understanding correlated electrons, but hard to solve.
So using Moiré systems to understand other difficult problems in physics.
Potentially, yes.
Yes.
Simulating high-TC superconductivity mechanisms, or exploring exotic theoretical concepts like fractons, particles whose movement is highly restricted. Moiré systems offer unprecedented tunability to perhaps realize and study these things directly.
That's a massive vision. And what about actual technologies? What's the practical promise down the road?
The potential applications are really exciting, though still mostly long-term. For quantum computing, those protected edge states in topological phases, like QAH insulators, are candidates for building fault-tolerant qubits, which would be a game changer.
Making quantum computers more robust?
Exactly. For low-power electronics, the ability to switch a material between insulating, conducting, maybe even superconducting states using just a small gate voltage is very attractive. You could imagine entirely new types of transistors or memory elements that are incredibly energy efficient.
One device, multiple functions?
Perhaps. In optoelectronics and photonics, those tunable Moiré excitons could lead to arrays of single photon emitters for quantum communication, new types of nanolasers, or very sensitive light detectors.
And information processing using spin.
Right, spintronics and valleytronics. The engineered magnetic states and the way electrons spin is often locked to its momentum valley in TMDs could enable new ways to store and process information, moving beyond just using electron charge.
And you mentioned strain earlier, too.
Yes, that's becoming a field in itself, wire mechanoelectronics. Using mechanical strain, not just twist angle, as another precise knob to tune the quantum states, it adds another dimension of control.
It really is a convergence of ideas.
It is. Twisting, stacking, straining. It's all about sculpting the quantum world at the nanoscale.
What an incredible journey. We started with emergence, this fundamental idea of complexity from simplicity. Then we dove into how Moiré superlattices let us engineer that emergence. That tiny twist creating giant patterns leading to flat bands.
The crucial ingredient, quenching kinetic energy.
Right, which then unleashes this cascade of level 2 and 3 phenomena, correlated insulators like Mott states and those amazing Wigner crystals.
Unconventional superconductivity popping up nearby.
Designer magnetism, even switchable with light, and these really robust topological states like the quantum anomalous Hall effect.
And not forgetting the Moiré excitons and phonons adding to the mix.
We also touched on the immense challenges in theory, fabrication, that painstaking tear and stack, and the sophisticated probing techniques like STM and AirPiece needed to see it all.
It highlights how cutting-edge this field is, pushing limits on all fronts.
But the overall picture is one of unprecedented control, isn't it? A new ability to design and tune fundamental quantum properties of matter almost at will.
It truly feels like we've opened a door to a new universe of emergent quantum matter, one that we are just beginning to explore and understand.
Which leaves us with a final thought for you to consider. If we can now engineer quantum states with this kind of precision, building simulators for fundamental physics models, what else could we tackle? Could these artificial quantum systems help us simulate and maybe even solve some of the longest-standing mysteries out there, perhaps in particle physics or even cosmology? What aspects of reality might we build on a chip in the future? Something to think about until our next deep dive.